Hello everyone, welcome back. In this video we're going to talk about one of the most important and interesting topic in the field of computer science, especially when it comes to learning data structure and algorithms. So today we'll be talking about big O notation and time complexity, what basically time complexity is. In the field of computer science, big O notation or time complexity is a theoretical measure of the efficiency of an algorithm, or it is a theoretical measure of the efficiency of a function in terms of the time it takes to execute as the size of the input data grows larger and larger. Imagine you have a big list of numbers and you want to sort them from smallest to largest number, or sort them from largest number to smallest number. Some ways of doing this are faster than others, especially when the list gets really bigger and bigger. For example, sorting large amount of data or numbers using a quick sort algorithm is faster than sorting a list of numbers using a bubble sort. So a big O notation is like a rating system that tells you how well the program or the algorithm handles large amount of data, like bigger and big list of numbers. So if you are working with a really big set of data, you would want to choose a method or an algorithm with a good or low big O rating, or with low time complexity. It's like saying the bigger the task, the longer it takes, but some methods handle bigger tasks better than other methods. So the big O notation or time complexity helps us understand how the performance of the algorithm scales as we increase the input size. So big O notation is one of the most important topics in the data structure and algorithm discussion. It is essential knowledge for software developers or software engineers. Understanding the big O notation can significantly improve your skill as a developer or software engineer, regardless of the company you're working for. Major companies like Microsoft, Amazon, Google, and Facebook, as well as smaller companies, often ask questions related to big O notation and time complexity concepts during the interviews. So big O notation, also known as big asymptotic analysis or asymptotic analysis, it helps us analyze the efficiency of an algorithm by considering its time and space complexity. It's not just about solving a problem. Every software engineer can solve a problem if enough time is given, but it is about solving the problem well and efficiently, minimizing the time required for execution and the space required for the algorithm. So using the big O notation, we can differentiate between poor quality code and good quality code. It allows us to evaluate the code readability, how easily others can understand and maintain our code, and also the code scalability, considering the growth of the input data set. So before diving into data structures deep discussion, it's important to introduce you to big O notation and time complexity, because it will frequently come up in later discussions and we might use it a lot in upcoming videos. So good or efficient code can be characterized by two main aspects: the readability and scalability of the code. So by readability, we mean the code should be clean and easily understandable by other developers who take a look at our code. And scalability, big O notation helps us analyze and predict how the code will perform as the input size grows. So by focusing these qualities, we can strive to write good codes that is both readable and scalable, enhancing the overall quality and efficiency of our software solution. So basically, there are different type of big O notation or time complexities. In this video, we are going to talk about some of the commonly used time complexities. For example, we have constant time complexity, we have logarithmic time complexity, we have linear time complexity, or we have linear logarithmic time complexity, we have quadratic time complexity, we have polynomial time complexity, we have exponential time complexity, or factorial time complexity. So let's talk about constant time complexity. The running, or is also called big O of 1. The time complexities are normally represented using the n variable or n notation. So we say big O of n, or big O of log n, or big O. We can use any name, but most programmers use n instead of x. If we want to represent a quadratic time complexity, so we say big O of n square, or polynomial time complexity, we say big O of n cube, etc. So to understand the constant time complexity, let's take a look at this graph. The running time of the algorithm or constant time algorithm is constant, and it does not change with the size of input data. As the size of input data increases, it doesn't affect the number of operations required to perform or execute the function. So if we take a look at the x-axis, x-axis represents the input size or number of elements given to our algorithm or function, and y-axis on the other hand represents the number of operations required to execute the function or algorithm. So for the constant time complexity, if we take a look, as the data set grows, the number of operations required to execute the function or algorithm remains constant. Say if I have one data element in my input data, so I require one operation to execute the function or the algorithm. If I increase the number of items by 2, still the number of operation is going to be 1. But if I increase it to 6, for 6 elements, still the number of operations to execute the function is going to be 1. If I increase it to millions, still it's going to be 1. So the increase in number of elements does not affect the number of operations or time taken by the function to execute. So that's why we call it big O of 1 or constant time complexity. So now let's take a look at logarithmic time or big O of log n. So the running time for this algorithm increases logarithmically when the data set or input size increases. This is a good time complexity because even for larger input size, the time taken does not increase drastically. If we take a look at the graph of logarithmic time complexity, we can see at the beginning it's going to increase a little bit faster, but as the input size grows and grows and grows, the number of operations required to execute the function increases very little or not drastically. So say for 3 items I may need 2 operations. For 4 items I may need 3 operations. For 10 items I may need 4 operations. So the number of operations increases very little. Then we have linear operation. Let's take an example of how if we increase the number of items in a big O of log n time complexity or logarithmic time complexity, how the number of operations required will increase. Say I have a data set of 4 elements. So if I take log base 2 of 4, so for 4 elements, so if I take log base 2 of 4, this is going to be log base 2 of 2 into 2 to the power of 2, because we write 4 as 2 to the power of 2. If I bring this 2 here, the power, so it's going to be 2 into log base 2 of 2. So log base 2 of 2 is going to be 1, so that's going to be 2 into 1, so that's going to be 2. For 4 elements, I require 2 operations. If I double the number of elements, say I have 8 elements in my data set, so if I take log base 2 of 8, log base 2 of 8, so we can write 8 as 2 into 2 to the power of 3. If I take log base 2 of 2 to the power of 3, so that's going to be 3. So if I double the number of items, so the number of operations increases by 1. Say if I again double that, if I make input size as 16 elements, so log base 2 of 16 is going to be 2 raised to 4, and it's going to be 4. So again the number of operations increased by 1. If I make it double and make it 32, which is larger data set, so the log base 2 of 32 is going to be 5. So this way, as the number of input size increases drastically, the number of operations required to execute the function or algorithm increases 1 by 1 or increases very little. So that's why we say logarithmic time complexity is better or best time complexity. Then we have linear time complexity or big O of n time complexity. The running time of the linear time complexity or algorithm with linear time running time increases linearly with the size of the input data set. As the input size doubles, the running time of the algorithm also doubles. If we draw a graph or take a look at the graph of a linear time complexity, so say for one item I need only one operation, so for two item I will need two operation. So the number of item in our data set increases, the number of operations required also increases proportionally. So if I have four items in my data set, so four operations will be required. If I have 9 items, so 9 operations will be required to execute the code or the function. So if I draw the line, we can see it's going to be a linear function. So the increase in number of elements is directly proportional to the increase in number of operations required to execute the function. Then we have linear logarithmic time, or big O of log n. So it is a midway between a linear logarithmic time and polynomial logarithmic time. So this is a polynomial logarithmic time. So this is better than a polynomial, but not better than a linear time. So for a smaller data sets, say this much data set, it is better than linear time complexity, but as the number of items grows for bigger set of input data, O log n, or a linear logarithmic time complexity, is not better than a linear time complexity. Then we have quadratic time complexity, or big O of x squared, but the convention is to use n to denote the big O notation, so we are going to call it big O of n squared, or quadratic time complexity. The running time of this algorithm is directly proportional to the square of the size of the input data set. This is common with algorithms that involves nested for loops or nested iteration, algorithms like bubble sort or insertion sort. So if we take a look at the graph of quadratic time complexity, say for one item I require only one operation, but for two items, so the square of 2 is going to be 4, I will require four operations to execute the function. For three items, since 3 square is equal to 9, I will require 9 operations, so for 3 items. But for 4 items, 4 square is equal to 16, I will require 16 operations. We can see for a small amount of input data increase, the number of operations required increases exponentially. So if I draw the graph of a quadratic time complexity, or big O of algorithm with big O of n square, so the function will look like this. With a small increase in the number of items, the number of operations required increases drastically. So this is not a good time complexity or algorithm. Then we have cubic time complexity, or a polynomial time complexity. We call it big O of n cube, or big O of n square. So the convention is to use n. The running time for this algorithm is directly proportional to the cube of the size of the data. This way, for each time I increase the number of item. So for 2, I will take the cube of 2 is going to be 8. For 2 items, this time I will need 8 operations. For 3 item, 3 cube is equal to 9 into 3, 27. So I will require 27 operations. So the graph for cubic time complexity is more steeper, and it is worse than a big O of n square, and big O of n square is worse than linear logarithmic time, and linear logarithmic time for bigger data set is worse than linear time, and linear time is worse than logarithmic time. So this way, as the graphs goes toward the y-axis, so the time complexity gets worse and worse. Then we have exponential time complexity. The running time of the algorithm doubles with each addition to the input size. This kind of time complexity is seen in brute force search algorithm. Then we have factorial time complexity. The running time of this algorithm grows factorial according to the size of the input data. This is seen in algorithms that generates all permutation of the given list or set of numbers. So let's take a look at an example of constant time complexity. If I open my Visual Studio, let me open this one. So say I have a function that takes a function or algorithm public, call it static, and let's call it get first item. So this function is going to take an array of integer, let's call it array. What this function is going to do is going to calculate the first element of the array and return it. So this is going to perform only one operation. So to calculate that, I'm going to say big O of 1 or only one operation. So let's define an array int array equal to 1 2. Say my array has only 2 elements, but if I call the function get first item and I pass my array to this function, so this is going to print 1. So the function only executed one line of code and returned 1. So but if I increase the number of input data, say I have 3, I have 4, I have 5, 6, 7, 8, 9 and 10, but if I still pass this input data to my function, it's still going to perform only one operation. So the increase in data set or input data set doesn't affect the number of operations performed by this function. That's why we say this function has a constant time or a constant running time. Say I want to return the sum of the first and second elements of the array, so I can define 2 integer values. Say I want to call it n1 equal to array of 0, the first element, and let's call n2 equal to array of 1. But what I'm going to do is I'm going to return the sum of n1 plus n2. So if we calculate the time complexity of this function right now, this is going to be big O of 1, and this is also going to be big O of 1. We will learn about calculating the time complexity of an algorithm or the function. One of the rule is that we will drop the coefficient of the time complexity. Say this is going to be 3 into big O of 1. So we have 3 operations. We drop the coefficient and we just take it, that's going to be equal to big O of 1. So if we take a look at the graph of an algorithm with 3 operations, say for one item I require 3 operations, for 2 items I require 3 operations, for 4 items I require 3 operations. So again, this is going to be a linear line or a linear graph. That's why if we have big O of say big O of 100, still it's going to be constant time complexity. If we have big O of 10,000 or millions, still this is going to be big O of 1 or constant time complexity, because one of the rule for calculating the time complexity is that we drop the coefficient of the terms. Say this is if we write that the 100 is going to be 100 into 1, so the 100 is the coefficient, so what we say, we drop the 100 and we take only 1. So big O of 1 is going to be the constant time complexity of these algorithms. So big O of 3 or big O of 2 or big O of 100 or big O of any constant number is still going to be a straight line or a constant function. All these big O notation, big O of 100, big O of thousands, they are rounded down to big O of 1 or time complexity or constant time complexity. So now let's take a look at linear time complexity or big O of n. So the running time of a linear algorithm increases linearly with the size of data. As the size of data increases, say I have another function, public static void. This function doesn't return anything. Void, let's print the number of elements. This is going to take an integer array. So what we are going to do, using a for each loop for each var item in array, we just want to print the item. So this is going to be big O of 1. So big O of 1 time complexity, or this is only constant operation, and this is going to run n times, where n is the number of items or the number of elements in this array. If I call this function print and pass my array, what it's going to do is it will loop through each element of the array and print each element one by one. So we can see 1, 2, 3 up to 10 is printed. So 10 operation is performed, but if I increase the number of elements by 2, say I have 11 and 12, so I added 2 items, 2 operations will be added to my function execution. So n times, previously it executed 10 times 10 into big O of 1. Right now, if I increase the size of the element by 2, it's going to run 12 times. So up to 12 it will print. So this way, as much as we increase the number of elements, the number of operations required to execute this function will increase. So if I have 1 million elements in my array, so 1 million times this big O of 1 will increase. So that's why we take 1 into n. So 1 into n. So we are going to put it inside the big O notation. So one rule of the big O notation is going to we are going to drop the coefficient, so we represent it as big O of n, where n is the number of items we pass in our input data sets. So linear time complexity means that the time taken by an algorithm or function is directly proportional to the number of input elements or input data size. So this is going to have a function like this. If I have another for loop in my print function, say for int I equal to 0, I less than array.length I plus plus. This time, before printing each element, I want to add one item, 1 to each element, then I will print it I less than array.length. Okay. So before printing that, I will say array of I equal to plus equal to 1. So I want to add to each element, then I will print it. So array of I. So this is going to be big O of 1. This is also going to be big O of 1 or 1 operation. So big O of 1. Let me comment this lines of code, and this is going to run n times, where n is the size of or the number of elements in my array. So in this case, we will be having n into big O of 1 plus big O of 1. So this is the time complexity of this algorithm or function is right now is going to be big. This we calculated is going to be big O of n, and this one is also going to be big O of n. We have a big O of n plus big O of n. So this is going to be 2 big O of n. So we are going to drop the coefficient. So as again, it's going to be big O of n time complexity. So this way we can calculate the time complexity of a linear function. Thank you guys for watching, and see you in the next video. Bye bye.